Welcome to this explainer on LightGBM. So today, we're unpacking exactly how researchers at Microsoft completely solve the massive data challenges that were just dragging down traditional gradient boosting models. If you've ever dealt with tabular datasets so impossibly large that they crash your system or literally take days to train, well, you are in the exact right place. Let's just dive right into this. Sometimes true innovation doesn't actually mean inventing something completely from scratch. A lot of the time, it means taking an already excellent idea and just making it faster, smarter, and way more efficient. And that's exactly what Microsoft engineers did here. They didn't reinvent the wheel. They took a phenomenal algorithm, gradient boosting, and engineered it to be infinitely more scalable. Think of it like this. You've got a high-speed train that works perfectly. But suddenly, instead of thousands of passengers, you've got millions. You don't need a totally new invention, right? You just need a lighter, higher capacity train that won't lose that incredible speed. So here is our roadmap for this explainer. We'll start with the big data challenge, move into the core innovations of smarter trees, uncover the secret to speed, learn about tuning the machine, and finally, we'll look at LightGBM in the real world. Section 1, the big data challenge. Let's start with why we even needed a new tool in the first place, when existing algorithms like XGBoost were already dominating machine learning competitions. Take a look at the sheer scale of the shift we've seen in data science. Back in the early days of machine learning, we were dealing with maybe thousands of rows. Finding splits was fast and easy. But today, we're talking about modern big data. When you're analyzing decades of nationwide wildfire data or millions of daily bank transactions, older algorithms just hit a processing wall. Searching for the perfect decision tree split across tens of millions of records became overwhelmingly time-consuming and incredibly memory-intensive. Moving to Section 2, Smarter Trees. To fix this massive data bottleneck, engineers basically had to lift the hood and fundamentally change how the algorithm searches for answers. Here's the really crucial point. It's all about how LightGBM handles splits. Traditional models evaluate every single data point to find the absolute best split. But LightGBM, it introduces histogram-based learning. So instead of evaluating 50,000 individual temperatures to find the perfect cutoff, LightGBM groups them into a fixed number of compact bins, say 255 bins. It evaluates the bins, not the individual points. This saves enormous compute time with practically zero loss in accuracy. Think of it kind of like a supermarket grouping apples by size categories instead of weighing every single one. We're simplifying the data to make it manageable. You don't really need to know that one apple is exactly 182 grams and another is 176 grams to know they both belong in the large bin, right? By summarizing the data like this, the overall pattern remains entirely intact, but the sheer amount of information the algorithm has to process shrinks drastically. Next up, LightGBM actually changes how the tree grows. Traditional models use level-wise growth. But rather than watering every single plant in a garden equally, lease-wise growth acts way smarter. It specifically targets only the branch that needs the most improvement. It essentially identifies the leaf that offers the greatest reduction in error and expands only that one. It's aggressive, it's incredibly efficient, and it focuses all that computational effort exactly where it matters most. Section 3, the secret to speed. Now, Microsoft didn't stop at histograms and leaf-wise growth. They actually added 2 brilliant turbochargers to make the algorithm run even faster. So, ask yourself, how should an algorithm actually spend its limited computational time? Imagine you're a teacher grading 10,000 exams. Do you meticulously review the papers of the students who got everything right, or do you focus your attention on the students who completely misunderstood the material? The ones making mistakes are where the real learning opportunities are, for sure. Well, LightGBM applies this exact logic through a feature called GAUS, or gradient-based one-side sampling. Just like an emergency room performing triage on patients, GAUS prioritizes the data points with large prediction errors, also known as large gradients. It retains all of these highly informative large gradient instances because the model still has a whole lot to learn from them. But for the instances that are already being predicted well, those small gradients, it randomly samples only a tiny portion of them. It then mathematically adjusts their contribution to maintain data balance. It's literally working smarter, not harder. On top of that, we have EFB, or exclusive feature bundling. This dramatically reduces memory usage by bundling sparse features that are rarely active at the exact same time, which saves incredibly valuable computing space. Real-world datasets often have hundreds of sparse features, just full of zeros. If you have two features that never overlap, why on earth store them separately? It's exactly like a shared parking lot in a city. Morning commuters use the lot, and then evening commuters use the exact same lot. Because they are never there at the same time, one shared space is completely sufficient. It's such a simple yet totally brilliant hack. Okay, section 4, tuning the machine. Now that we've built this incredibly fast machine under the hood, we really need to learn how to properly drive it. Think about it like this. Owning a Formula One race car doesn't automatically make someone a champion. Success comes from knowing how to adjust the machine for the track ahead. Just like adjusting the suspension, tires, and aerodynamics on that race car for a very specific track, tuning LightGBM is absolutely essential for a good outcome. The algorithm is remarkably powerful, but it's the hyperparameters that dictate how effectively it navigates the unique twists and turns of your specific dataset. These specific hyperparameters control the model's learning behavior, ensuring we balance prediction accuracy without just, memorizing the training data. The learning rate controls your step size, and that works hand in hand with the number of trees. Because LightGBM grows leaf-wise, the number of leaves directly dictates your tree's complexity. You use max depth to put a firm ceiling on that aggressive growth. And finally, minimum data in leaf ensures that every single leaf represents a broad pattern rather than just one highly specific overfitted data point. Now, you might be amazed to see that despite all this highly complex engineering under the hood, implementing LightGBM in Python actually takes just a few surprisingly straightforward lines of code. You split your dataset, define the model while passing in those key hyperparameters we just talked about, fit the data, and generate your predictions. All that incredible Formula One engineering is neatly packaged for you to use in literally seconds. Finally, Section 5, LightGBM in the real world. Let's take a look at where this algorithm actually shines out there on the track. From modeling nationwide wildfire pollution over decades to identifying fraudulent bank transactions in a sea of millions, LightGBM has become the absolute go-to for massive structured tabular data. It gives researchers and businesses the real-world ability to process enormous volumes of complex nonlinear information efficiently and importantly without breaking their hardware constraints. While deep learning pretty much completely dominates unstructured data like images, for structured data, it's really a showdown between the trusted stability of XGBoost and the sheer unmatched speed of LightGBM. XGBoost offers balanced, conservative tree growth that is perfect for smaller datasets where maximum stability is paramount. But when data sizes just absolutely explode, LightGBM's histogram binning and leaf-wise optimization make it an absolute powerhouse for rapid training and incredible memory efficiency. So, the next time you face millions or even billions of rows of data, you really have to ask yourself, are you taking the standard highway or the LightGBM expressway? Selecting the right algorithm isn't just about finding one perfect tool for every single job. It's about understanding the internal mechanics so you can apply the exact right tool for your specific challenge. Thank you so much for joining this explainer, and I honestly can't wait to see what you build with this incredible machine.